Welcome to the Explainer. Today, we're going to crack the code behind all those swooping curves and fluid motion you see everywhere. We're going to learn how to read the blueprints that bring them to life, and those blueprints are polynomial graphs. So let's start with a fun idea. What if a math formula wasn't just, a boring equation on a page? What if it was the actual blueprint for an epic roller coaster? I mean, all the ups, the downs, those gut-wrenching twists, it's all right there, hidden in the math. Okay, so before we can build our masterpiece, we gotta know the rules of construction, right? For any ride to be safe and fun, the track has to follow some really basic principles. And guess what? Polynomials have rules too.
Check this out. Just like a great roller coaster, polynomial graphs are always smooth and continuous. You're never going to see any sudden, sharp corners. No way. And there are definitely no gaps in the track. The whole ride is just one beautiful flowing curve.
Think about any great roller coaster. It always has those heart-stopping moments where it swoops all the way down to ground level. Well, in our mathematical blueprint, we call these points our zeros. And they are, quite literally, the foundation of our entire design. So these zeros, you might also hear them called x-intercepts. They pinpoint exactly where our coaster track either crosses or just touches the ground. Finding them is the very first step, kind of like setting the concrete pylons for the whole structure. So how do they find every single one of these ground level points? Well, we've got a simple but super powerful tool in our engineering kit for this. It's called the zero product property. This sounds a little formal, but the idea is actually super simple. If you're multiplying a bunch of numbers together and the final answer is 0, well, at least one of the numbers you started with had to be 0. There's no other way to get there. So here's the game plan. First, we break our big polynomial blueprint down into its smaller individual parts. Then we take each of those little parts and set them equal to 0. And just like that, we can solve for every single point where a ride meets the ground. Simple as that? But here's where it gets really interesting. Knowing where the ride hits the ground is only half the story. The blueprint also tells us how it behaves when it gets there. And it even tells us where the ride starts and where it's going to end up. So our next clue is a little something called multiplicity. All this really tells us is how many times a specific factor shows up in our blueprint. And that clue is the key to knowing exactly what the coaster car does at each ground level point. Is it going to be a smooth pass-through or a dramatic bounce? And it's honestly as simple as this. If the multiplicity is an odd number, like 1, 3, or 5, the coaster car just slices right through the ground level. But if it's an even number, like 2, 4, or 6, the car comes down, kisses the ground, and bounces right back in the direction it came from. Pretty cool, huh? Okay, one last piece of the puzzle. Our blueprint has to show where the cars enter the track and where they fly off to after that final drop. This is what we call end behavior, and it's all about the ride's big picture journey. And this little chart here, this is basically our cheat sheet for end behavior. You just look at the very first term in the whole polynomial blueprint, and you can instantly tell the ride's entire trajectory. So for instance, if it has an even degree and a positive leader, you know the ride starts way up high on the left and ends way up high on the right, kind of like a giant U shape. All right, so we've got all our pieces. We know our ground points, we know if it's a bounce or a cross, and we know the end behavior. Now we can actually sketch the entire ride. And these ideas don't just apply to roller coasters. They're used in real-world design and construction every single day. It really boils down to this simple 4-step process. You mark your ground points, you figure out the behavior at each one, bounce or cross, you establish the start and finish lines, and then you just connect everything with a smooth, flowing curve. And boom, you've just sketched a polynomial graph. Okay, roller coasters are cool and all, but you might be thinking, when am I ever really going to use this? Well, you'd be surprised. These exact same principles are used all the time in design and manufacturing to optimize for things like space and materials. Let's take something super simple, like a cardboard box. So here's the challenge. Imagine you have a flat sheet of plastic, and you want to cut squares out of the corners so you can fold up the sides to make a box. The goal is to get the biggest box possible, the one with the most volume. So the big question is, how big should those cuts be? Well, the volume of that box can be perfectly described by this polynomial right here. And here's the magic. By graphing that polynomial for the volume, we're basically looking for the highest point on the curve, right? The peak of our volume roller coaster. And the graph shows us, clear as day, that the maximum possible volume is about 339 cubic centimeters, and we get that by cutting squares that are just about 2.7 centimeters on each side. No guesswork, just math. So you see, a polynomial is so much more than just a formula. It's a powerful blueprint. It's a language for describing the world around us, from the thrilling arc of a roller coaster to the optimal volume of a box. It's a language for building, for optimizing, and for understanding the shape of things. So the only question left is, now that you can read the blueprint, what are you going to build?